right. So finally. Okay, so today is about logistic regression, which is an extremely important topic. It's more like it's very important classifier. Move from connecting the regression to the classification, and also it's the basic unit built for as a component in the deep learning, the modern deep neural network pipelines. So logistic regression. So to talk about logistic regression, again, we are in the classification, and there will be a little bit of learning theorem today. So today I'm going to actually start from base classifier. The logistic regression is just one kind of base classifier. And then I'm going to cover what do we mean logistic regression and how do you formulate a loss function of logistic regression, and then how do you solve it. And the solution optimization will be mostly covered in the next lesson when we talk about neural nets, because it's mostly what we're going to cover is stochastic gradient descent when you have a multi-layer type of neural nets. So logistic regression, you can think about it's really just one unit of the deep neural network. Okay, so base classifier. So base classifier, you can think about it's more umbrella group of classifiers uses this rule to perform classification. So we actually reviewed in the last lesson about probability, and also we reviewed it's all those type of probabilistic models. They can all just goes into three different kinds. Do you want to estimate joint probability, or marginal probability, or conditional probability? And in fact, base classifier is totally just about a conditional probability. The conditional is the output variable, conditioned on the input variable. So we treat all the features as random variable. So we're using a probabilistic formulation to perform classification. And the classification rule is, so because we have, so our output variable in the classification case is a discrete variable, right? So it has number of possible values. And the best classification for a specific sample is the one maximize this conditional probability. So P, C, Cj, so they're C1, C2 until Cl. So assuming it's a multi-class classification, so there are total, so now I'm changing from Y to C just to kind of distinguish and make the concept a little more clear. So our output are classes. So they're C1, C2 until Cl. So this is the set of possible classes I'm trying to predict. And I'm trying to use data to estimate the conditional probability, PC sub j conditional x. X is actually, in fact, the p different feature variables. And j is here, is j belongs to 1, 2 until L. So the one actually who maximize this conditional probability is my predicted C star. So this is the rule we're going to use called the MAP rule. And if you use probability formulation to model the relationship of input and output classification, and you're using this max rule, and this type of classifier is called base classifier. So just more detailed, we treat each feature variables and also class label as random variable. So kind of review ourselves, what do we mean random variable? So we actually reviewed there's event space, sample space, random variable, we just project elementary event from the sample space into some kind of attributes. And then in this case, the class variable, that output variable, they're C1 onto CL, different values. So this is the specific C random variable, output random variable. And for each feature, it depends on the properties of the feature. So it can be discrete, it can be also continuous. And during the testing stage, how do you use it? And it's, so when you're given a sample with the specific attributes x1 onto xp, and you're going to find the class that maximize this p condition on c condition on x. So here, so c belongs to the c1 onto cl. There are L different possible values. And during the training, it's you want to estimate, you want to figure out how do you estimate this from data. So this is the question in more concretely, different kind of base classifiers using different type of formulations to model the conditional probability. So just to emphasize about that testing rule, this is called MAP rule, maximal posterior probability rule, and base classifier uses this MAP rule. So then even more concretely, because previously I do argmax, which sounds not concrete, so let's make it even more concrete. So for all this different C1 onto CL, you just compare. And you compare for every C sub J, the one give you the biggest probability is the C star, which is reflected by this formula. So the PC condition on C star is the one maximize the formulation. Question about this? It's an easy rule, but I just keep saying again, because there's, whenever we talk about probability, there's some student needs needs more time to get familiar with the formulation, the equation. And this is a discrete variable, so we actually know what. Summation of P, C condition on C sub J, J from 1 to maybe L, condition on, so if you still can remember, we can simplify the notation by dropping off the variable and only leave the attribute. So this is how I'm going to write it. So what is this? Summation of P, C equals to C sub J, J loop over 1 to L, condition on X, which is what? 1. Because, yeah, it's all the sample space, right? This actually is all the possible values. So its summation is 1, and then we're using the largest one, the one giving me the largest as the predicted class. Okay, so like I told you, in the end, this is just using a probabilistic model for classification. And we already mentioned conditional, this is actually conditional probability, right? So if the conditional probability is can be easily directly estimated from the data, we just directly use that formulation. And this type of model is in fact called discriminative base classifier. If this is harder, it's actually not easy to be directly estimated from data. So when conditional probability is hard to directly estimate from data, what rule do we use? Conditional. When the conditional is hard, we use we just covered last in the last lesson. Conditional probability use Bayes rule, right? So when conditional, it's harder to directly estimate from data, we use Bayes rule. And that's actually, so this, I'm going to derive you later the reason why we converted from this conditional into this joint and then later into this chain rule formulation is, so I will cover later, but just not to confuse you, is Px condition. So this is called generator classifier. The whole generator classifier makes use of Bayes rules. So you use Bayes rule, and then you are doing argmax. When you're doing argmax, actually the denominator doesn't even influence the max operation at all. So that's why you drop it. Because Px is not related to the C, and you're trying to argmax only the C, so that's why this denominator doesn't matter. It's all proportional with the 1 over Px, so that's why you change this argmax from Pc, conditional x, into argmax Px and C by dropping off the Px denominator. And this is a whole idea behind various kind of generative Bayes classifier. And we're going to cover that later after we finish the discriminative classifier. All right, question about this? Discriminative classifier directly model this conditional probability from data, from using some kind of parameterized form. And logistic regression is exactly one kind, follow this. And there's another kind using not directly estimating C from X, but indirectly from using the Bayes rule from this, actually in fact, the X condition on C, this is called a generator classifier, which is a really big group of classifier. All right, so why? So your first question will be, I speculate is why MAP rule is a good rule. So in fact, you actually can prove it. So we try to cover the Bayes and variance trade-off. If you remember this page, we try to decompose the whole area, which is called the expected prediction area, which is considering all the joint probability, not just the y or not just the x, is the joint probability of x and y, and then taking expectation over that function is the loss function L. And in the L2 case, we actually proved this give you, you can decompose it into Bayes and variance and trade off in the regression case. And if you change that loss function, not using L2, but instead using some loss called 0-1 loss. So 0-1 loss is the most classic loss for classification, right? If you predict it correctly into the target correct class, its loss is 0. There's nothing to lose. If it's not a correct prediction, you will contribute 1, which means it's a wrong prediction in the total loss accumulation. So if you use 0-1 loss in the expected prediction area, considering all the joint probability, the classifier you're going to get, the best classification rule is the MAP rule. Question about this? This just gives you a reason why we use MAP rule. So among all the possible output label, possible values, the one give you the largest probability is the classifier minimize the EPE, expected prediction error. And in fact, you can actually prove it, and this is the proof. I tried to do quickly, and there's, I'm going to put a link from the Element of Statistical Learning book. It has a few pages prove this. So it's actually not very hard. I mean, let me go really, really quickly so you try to replace this error, this L, C, and Fx into a confusion matrix kind of error. If it's predicted correctly, it gives you 0. If it's predicted wrongly, so it gives you actually, in fact, a matrix, right? So if it's predicted correctly, it's 0 loss. If it's predicted wrongly into any other class, it will contribute 1 loss. And point-wise, it's you read by yourself, and this gives you the best predictor is the MAP predictor, the one maximize the probability, the class label maximize the conditional probability. All right, so like I said, the base classifier uses MAP rule, and there are different kinds of base classifier. So in the end, base classifier just using a probability formulation to convert X to Y, right? So everything we learned before is X to, in this case, I just change it to C, just make it more clear. This is classification, and we are using some strategy is conditional probability to as our old F function. So instead of a generic Fx, we're using probability formulation to formulate the classification, and this minimize the 0-1 loss on the expected prediction error. If you try to maximize expected prediction error, so then the whole thing is how do you represent Fx, right? How do you represent Fx? And in this case, how do you represent P, C conditional X? The discriminative classifier just directly, so this is still like a black box. What do you mean? So here is, when you're given the feature variables, I directly output a vector. It's PC1 given X, PC2 given X, onto PCL given X. So it directly modeled the conditional probability. But what is it? So to give you an example, the most classic discriminative classifier is logistic regression. So to review, logistic regression has this formulation. So this is just a 1D case. So like I said, base classifier, discriminative base classifier directly model PC conditional X, right? Here is, again, binary variable, y equals 1 or y equals 0. I'm directly modeling that conditional probability through this formulation, through a function. So this is what I meant, discriminative model. So because this is a binary classification, right? So when you have py equals to 1, conditional X, and then it's equivalent to, you already know py equals to 0, because it's equals to, like I just told you, the summation is 1, so that's why getting py equals to 1, equivalent to, you already know, py equals to 0. This is for binary classification, okay? So, and this is a pretty magical form, right? So what is it? So let's kind of recap from the regression. So our regression formulation is y equals to beta x, right? It's just beta x, it's the linear regression. And logistic regression is almost the same, but just changing the left side into a function called logic function. So the right side is still a linear form, linear combination of the inputs. The left side, this is called the log odds of the conditional probability. So this still, so in the end, the whole logistic regression is, I am assuming the ratio of P, so we already said this is y equals to 1, right? So this is equivalent to py equal to 1, conditional probability, y equal to 0, then take a log. So the ratio of the probability equals to 1 over probability equal to 0 and take a log is a linear form. It's a linear combination of input x features. That's the assumption you're making of logistic regression models. Okay, so but what we understand linear regression, but like I told you, everything here is about conditional probability, right? What do that conditional probability looks like if you have this assumption? If you assume the log odds is linear, and it's very easy, you can derive it, and it's equivalent to the conditional probability is this formulation. You can simplify it, and this is actually called, it's a sigmoid function. It's a sigmoid function on the linear summation of x. So geometrically, let's see what geometrically it looks like. So because one has multiple dimensions, it's too difficult to visualize. Now let's go to one-dimensional x, and then y, and this is the surface map. So in the one-dimensional case, py conditional x is e alpha plus beta x over 1 plus e alpha plus beta x, right? So it's really just a little bit simplification by only have one feature. And then again, you can write it as two different views. Either it's the logic view or it's a conditional probability view. So let's look how it looks like. So we normally call this logic of p, y given x. So that's also the reason why, and this is called logistic regression, because the logic is a linear regression. You assume the logic of this conditional probability is a linear form. All right, so geometrically, so this is the logic function, right? So from the previous page, this is p over 1 minus p. So the p here is just y equal to 1, condition x. So log p, 1 over p is, of course, is linear, right? Because this form is linear. It's alpha plus beta x. And then if you draw it geometrically, it's probability py conditional x, py equal to 1 conditional x. In fact, it's an S-shaped function. So S-shaped function. So it's very easy to remember the logistic conditional probability. This function it has an S shape. It's an S-shaped function, has the bound. So the largest value is 1. Smallest value is 0. And of course, right, we have the axiom from the previous class. If this is a probability, of course, it should be bounded from 0 to 1. And in the end, this formulation just guarantees the output is a bounded 0 to 1 number. So, but parameterized, controlled by both your feature x and also two parameter alpha and beta. So, and then I'm actually putting a heads and tail here. It's in fact, the whole assumption of logistic regression is what? It's your output variable. It's a binary random variable, right? Like base classifier. Base classifier assumes y, assumes c, assumes x. It's all random variable. But when you talk about random variable, there has to be some kind of probabilistic assumption you're making. And in the logistic regression case, you're assuming what? You're assuming the output variable is binomially distributed. Sorry, sometimes I use C, sometimes use Y. A little bit confusing, but in this context, yeah, it's just output variable. Why in this case, it has only two possibilities. 0 and 1, or heads and tail. And so if you remember what we said, when you talk about Bernoulli distribution, so what is the parameter of a Bernoulli distribution? So I'm flipping a coin, and to model a Bernoulli distribution, I need parameter to represent that distribution, right? What's the parameter to specify a Bernoulli distribution? The P. So what's the probability of being head? So whenever there's in the Bernoulli distribution, and your parameter is that P, right? P hat. And of course, P tail is 1 minus P hat. All right, let's just see now. In fact, logistic regression just specify P hat using a parameterized function form. So the P hat in this case, or P hat is 1, let me just switch it to not get you confused, tail and head. Instead of, the most cases, the basic Bernoulli, we normally are trying to estimate, we flipping the coin many, many times. If there x times over n times is heads, and we were going to assign the P as x over n, right? But in this case, we don't assume it's a scalar, we assume it's a function. And this function is controlled by x. So, question about this? This is very, very important. So, in the basic Bernoulli, we're just using counting to estimate P hat, right? We don't assume that P hat is related to anything. It's a constant. And you use the observed traces of head and tail to estimate it. But in the logistic regression case, you're assuming P hat is a function. It's a parameterized function controlled by the input feature. Again, so P hat, so it's the S form, it's a function parameterized by the x, so which controlled by x and also alpha beta parameter. And so just to connect, if alpha plus beta x, you're going to get minus infinity to positive infinity possible values. And then when you have this function, it's guaranteed to be bounded inside 0, 1. So it's like two different views. Either is squashing the output into 0, 1, or the other view is it's parameterized the P hat using the x. Question about this? Squashing view or probability parameterized Bernoulli distribution view. All right. Okay, so this is all like a probability, right? It sounds a little bit daunting to understand, but so because it's classification, right? And then what do we mean classification? So let's just see. I'm trying to estimate P. So my first question is, my output is, there are two cases, binary heads and tail. or 1 or 0. So what do I mean the points on the decision boundaries? So try to remember from the SVM case. So in the SVM case, we try to have find a boundary or a margin, not just a line. So in the SVM case, we try to specify that boundary as a 0, right? If you remember, W transpose X plus, sorry, it's bad writing, plus B equal to 0. So this is the SVM case. And we just assume that. We assume, we make assumptions of the boundary is 0, and then the left touching margin and right touching margin is -1 and +1, and we try to look for W and B from data. So that's the SVM case. So because now we're using probability, so in the SVM case, we know who are the decision boundary points. And in the probability case, and what's our decision rule? Our decision rule is argmax, specific y values, 0 or 1, p condition on x, right? So if we're using a probabilistic view, what should be the points, the properties, if they are on the decision boundaries? A point on the decision boundaries, which means what? It's on the decision boundary, which means I can't decide. And from a probabilistic view, what type of points you cannot decide? Because the rule we are using is argmax, right? It's the one maximize. Which type of points you can't figure out which one maximize, which class label maximize. If there's only 2 cases, it's very easy. Which means what?
45.
Yeah, and which means for a specific point, for those points, Py equal to 0, conditional x, equals to y, conditional 1, equals to 1, conditional x. And in the binary classification case, these are the points on the decision boundary, right? Because everything we are relying on now is a probabilistic representation. And we're using argmax to loop over all the possible y values. But if every number, no matter what y, give you the same value, and you can't decide, there's no way for you to decide, right? So this is the decision, the point, and this type of points are the decision boundary points. All right, so let's see. This means what? So for logistic regression, there are 2 different formula, right? Let's go back to see this. 2 different views to think about logistic regression. First view is its conditional probability is this type of weird function. The other view is this logit, the log odds of p over 1 minus p is a linear form. So that's, okay, keep this in mind, memorize it, take screenshots. Let's go to this page. All right, so what is the logit form of logistic regression? Log p y equals to 1 over x over p y equal to 0 over x, which is 1 minus the upper. So all logistic regression follows what? Follows this equals to the linear case is upper. Let me just write a generic case, just beta vector transposition with the x vector. Oh God. Okay, so this is the generic form, right? then for those points on the decision boundaries, because they satisfy this, right? And then this means what? Put this here, put this here, and they equals to each other. And then that means points on the decision boundaries guarantee beta transpose x equals to 0. And this actually defines a hyperplane in the p-dimensional space, which means what? The logistic regression also learns a linear decision boundary. Okay, question about this? So even though we are using a kind of probabilistic formulation, but in fact, the decision boundary, it's still a linear line, a linear hyperplane in the high-dimensional case.
So I didn't understand that why log of p upon 1 minus p is coming out to be a linear function. I mean, how?
This?
Yeah, so how this came out to be a linear function?
Yeah, so it's because of, okay, so when they're the decision boundary points, and I know that, right? And this means what? Py equals to 1 conditional x over py equal to 0 conditional x equals to 1. And then I put in here, so this equals to 1 for decision point. Log 1 equals to what? Know that question?
No, not that question.
Okay, sure. Yeah, what question?
Question is, I mean, you assume that log of p upon 1 minus p, this entire function will come out to be a linear function.
Oh, you mean this assumption?
Yeah, so.
This is my assumption.
I mean, how?
Why that's a good assumption?
I mean, why does assumption holds in general case?
It's the assumption. It's like a linear regression. Why linear regression holds? Right? It's about your data. It's the domain knowledge. If this gives you the good prediction performance, that means your data, this assumption holds for your data. So in the end, no matter what algorithm we are learning, you are making certain assumptions. And here, this assumption I'm making in the logistic regression case is this assumption. The logit is a linear form. That's my assumption. And you can convert this, you can actually, in fact, this assumption means my decision boundary is a linear separation hyperplane. And that's an easier, intuitive way to see this. They're the same way, just one is a probabilistic way to say, and the other way is a geometric way to see that. So the geometric view, it's more intuitive because you normally can think about it, right? And this is to connecting from a probabilistic formulation. All right. So in the end, you are assuming your decision boundary is linear by this formulation. And if you're connecting to SVM, SVM has no probabilistic assumption. It just assumes decision boundary is linear, and also there's a margin. And you're trying to estimate WNB that best separate the two classes. And here, it's actually very similar too. I'm just assuming my logit of conditional probability is linear form. And I'm trying to learn the best beta to fit the logit of y conditional x in my data. And I'm trying to learn the beta. All right, so this is almost a repetition what I just covered. So log p over 1 minus p is a linear form because the decision boundary point p1 equals 1 equivalent to y equals 0, and this gave me 0. The decision boundary makes this 0. This guarantees the decision boundary to be linear hyperplanes. Okay, so once you use logistic regression, so you should code your output label as 0, 1. Like I said, And we are using Bernoulli distribution, right? Bernoulli distribution to represent, to model our output conditional probability, Bernoulli distribution, which exactly showed here, head and tail. Sorry, this is not correct. It should be Py given x. Yeah, y equals to 1, conditional x, and the other is, so no. It's not Px, it's Py equals to 1, conditional x. So again, we are directly estimating this conditional probability from the data by assuming it has certain functional form. And we'll observe 1 and 0 for the target variable conceptually as probably that 1 will occur, almost the same as head will occur. Yeah, it's the same. So I already talked about this. So the whole idea is it's a Bernoulli distribution. The Bernoulli parameter is a function controlled by both the parameter alpha, beta, and the specific values of x. And we use Bernoulli distribution to model the target variable with its Bernoulli parameter predefined with a functional form. And the main interest is to predict the probability that a event occur, which is Py equals to 1 given the x, because for a Bernoulli distribution, the only thing we need to know is P head. So in the end, just to emphasize, this is just assumption. You're assuming the logit of the P y given x is linear, equivalent to you assume the decision boundary is linear. And there's no assumption about feature variables is linearly related to the target variable. So different from the linear regression y is linearly related to the x. Here it's not. It's through a logistic representation. So there's no linear relationship with the output y and x. So don't get confused there. Okay, to summarize, there are two different views. The first view is a squashing function. It squashed this type of alpha plus beta x from minus infinity to positive infinity into 0, 1. That's the first view to think about logistic regression. The second view is the logit of the p hat is a linear function. Two different views, but the same model. Sorry, again, a mistake here. So it should be I'm going to fix those. Yeah, it's p y 1 here is 1 minus p equals to 1 conditional x. So it only models conditional probability. Okay, so how do you train it? So I talk about all those probability formulation and in the regression case, we just use, it's very natural to use L2 type of loss, right? But when you talk about probability, and it's, how do you model the loss, right? And there's a lot of nicely theoretical, so when you have probability type of formulation, it mostly will use the maximal likelihood based estimation based formulation to model the scoring function, model the loss function. That's just one. It's a good formulation, proved good for when you have a probabilistic type of modeling. So what is MLE? So MLE is you're considering, because you're assuming your output variable and input variable are all random variable, right? So in our case is assuming it's there's a z variable. In fact, our z variable, z vector variable includes x1, x2 until xp, and also that output c. I can write sy too. So this is a vector of random variables. For each random, this vector random, the random vector, you will observe observed initialization. It's actually is your training data. Your training data has n pair of x and y. which I'm representing as Z1 until Zn. And they are drawn from a probability distribution is PZ given theta. So here just you're assuming they're generated from some kind of probability distribution. And the whole goal is you're trying to estimate theta by feeding this probability distribution to this probability distribution to the data. So then how do you do it? And you're trying to maximize the drawn probability. So here, the Z1, assuming the Z is the first observed initialization of that combination, and you observe Z1 is the first training sample, second training sample until the nth training sample. I'm drawn because I have a way to model the probability, right? I have a way to model each sample's probability, and then I'm observing n different kinds. And then what is the drawn probability? Very easy. Drawn probability is just this PZ1 until Zn given theta. Because we normally assume all the training samples are independent, are identically distributed, so which assume they are independent from each other. So the drawn probability of all the training samples equivalent to multiplication of each samples given that probability distribution model. And all those are shared using a shared parameter given theta. And then you just trying to do argmax. You're trying to maximize this drawn probability, looking for the theta, maximize this drawn probability. That's exactly maximal likelihood estimation. So I'm trying to represent all the training sample together as a drawn probability because they are independent from each other. So that's why this drawn probability decomposed into multiple multiplications. And then you're trying to maximize this. You're looking for the theta, maximize this. And this whole procedure called maximal likelihood estimation. It's very easy, right? So it's just in the end, drawn probability of many samples. So you're trying to do argmax theta, and this is how you estimate the unknown parameters by maximize the drawn probability. We call this drawn probability as data likelihood. So let's do step by step. You're assuming a particular model with unknown parameter theta, and then you define a probability of observing a given event. So you observe a given event, condition on that theta, which is PZI condition on theta, and then you observe a set of the events in the real world, which is Z1 until Zn. And then you try to maximize this drawn probability, which is this drawn probability by tuning the theta, by argmax the theta, and this theta is the MLE solution. So in most cases, and this MLE solution is consistent and efficient, and the majority of our cases, we don't directly use data likelihood. We normally use log data likelihood because when n is really large, this is a lot of multiplication, right? And also each one of those, because that's a probability, we actually reviewed the axiom of probability is bounded from 0 to 1, right? If there are so many smaller than 1 positive number multiplied together, and it's very likely to have numerical issues. Just go over the floating the resolution a computer can represent. So that's why we normally use log, so the multiplication of this, the multiplication of each data likelihood will convert it when you do a log into a summation. And also because the log function is a monotone function, so the theta, the argmax here, theta here, it's the same as the argmax theta here. So it's monotone because log is a monotone function. So it's converted from a many multiplication into a summation of log on probability. So this is a very popular, actually almost always using this trick to guarantee numerical stability when you work with this type of probabilistic models. Question about this? All right, so again, it's the PZ, right? So we call this normally likelihood, and we call this log likelihood. So now let's come back to see our problem. So I'm starting from a basic Bernoulli, not the Bernoulli we are using in logistic regression, just a basic Bernoulli. So actually, let me just think, this is Z. So you're doing flip the coin, you're observing head, tail from n different observations. And you can rewrite it as 1 or 0, and head is 1, tail is 0, and the Boolean parameter in the Bernoulli distribution is what? So P Zi. So PZI, so Bernoulli distribution has this probability formulation, right? So if it's a head, it's going to give a P, so it's equivalent to, if I'm observing a head, the probability is P. If I'm observing a tail, the probability is 1 minus P, right? But how do you use a joint representation to represent two cases? If Zi, so let me make it more concretely because it's not that straightforward. If Zi is head, and also in our case is 1, it's P. If Zi is tail, it's 1 minus P. And you can, sorry, I used X, but yeah, let's just use X. It's the same as the Z, just to make it clear. So this kind of case of branching type of representation is totally summarized by this, right? So if it's head, its number is 1, and this will be 1, and this will give you, because this is 1, this gives you 0, this part is 1, right? And then this whole condition, this probability is P. And if it's a tail, it means Xi is 0. 1, this is 0, and this part gives you 1. And this part, so this is 1, so that's why the probability is 1 minus P. So this summarized representation is exactly this. So don't get confused. Okay, so P is the parameter you're looking for, right? It's the P. So what is P here? That small p is the Bernoulli P parameter. So our goal is actually the theta. Our theta is the P. Is that probability head, is the P hat. This is the basic Bernoulli. in the Bernoulli case. Right? So go back to MLE. So you have a theta, you have a parameter, parameterize the probability distribution for each sample. And in our case, that theta is the p hat. We use the small p to represent it. And this is your data likelihood for specific data. So when you have many, many data, in fact, your data likelihood is just multiplication from I from 1 to n p xi 1 minus p 1 minus xi, and then you do argmax. You try to maximize this, looking for the best scalar p to maximize this data likelihood. So this is basic Bernoulli, right? Basic Bernoulli. It's a constant parameter. So here p is a constant. All right, so now let's move to logistic regression, which is a parameterized Bernoulli. So I already repeat the previous page. So this is the basic Bernoulli for each sample. And this is for all the samples. So now let's move to logistic regression. So logistic regression is what? Logistic regression is p y equal to 1 given x. It's a parameterized p, which is some kind of function. It's exponential of beta vector transpose x vector 1 over exponential beta vector transpose x vector. And I want to do the same thing like this. The only thing changes is to replace that constant p in the basic case with a function form. Has both the beta parameter and also the x input. So in the end, what is my, so if in this form, who is my theta in this case? Theta? Theta is theta vectors. So I'm trying to, in the end, because I'm given training samples, a lot of training sample is x1, y1, x2, y2, until xn, yn, right? And my probability is exactly this. But this is only in the one case, right? There's also the okay, so let me explain further so if you see here, there's head and tail. So the head and tail is the x, right? It's those observed numbers. And in our case, what we observed is the specific x1, and that specific y, and y can be head or can be tail. It can be head or it can be tail. Maybe x2 case is tail. So how do I write out the function of because there are two cases of probabilities. So here x, it's a little bit confusing. So this just represents the current, but it's the z in the previous page. Don't get confused. It's just trying to show it's the z. Yeah. Yeah, sorry, it's a little bit confusing, but okay. So in this case, so this is only P head, right? But I need to draw also the tail case. It's actually here. So I need to draw two cases and to summarize my probability. So P, my current observed Y, observed YI, it can be 1, can be also 0. It equals to two cases. If yi equals to 1, if yi equals to 0. So if yi equals to 1, and it's that p minus 1, which is, so if we come back here, so if it's this formulation, if equals to 1, it's this formulation. If it's equal to 0, it's actually 1 minus this formulation. So I want to have a summary representation to summarize two cases, which is e beta x over 1 plus e beta x, or 1 over 1 plus e beta x, which is the 1 minus p equals to 1. So because now I have this representation, now I can write out the joint probability now. So my samples are, so I have, my samples is many samples, then my joint probability likelihood, my likelihood is the multiplication of I from 1 to n samples, p yi conditional xi, and also parameterized by that theta parameter. And this is how you write out the likelihood. And then you do argmax of this logistic regression to learn that theta. This pen is not easy to write. So, and then this can give you argmax, and which is give you the best theta, which is actually in fact the theta. So this is just pretty abstract. In fact, what you derive here is this formula. So I'm trying to write out the log probability, right? Because the probability is just too, log probability is easier to write. I converted the multiplication of many multiplications into summation of log. So this is the generic. And then I write out what is py given x, and there are two cases. The first case is if yi equals to 1, this is the representation. If yi equals to 0, and this is the probability, if you see here. So if it's 1, it's log p. It's directly do this. If this is 0, and it's this just take log. So yeah, it's the same as that before. So yeah, maybe easier for me to write here. So if I'm taking the log of this log likelihood, it gives me a summation of, it will convert it into, if it's a log likelihood p, it would be look like summation of xi log p plus 1 minus xi log 1 minus p. and which is actually this form. So I have py equal to yi, and I don't know if it's head or tail. If it's, and then you use a summation form, which is the p of that Bernoulli parameter has the power yi and 1 minus yi, and then times the 1 minus the 0 case, and then you take the log and put the yi before, and this is yi log plus 1 minus yi log, which is exactly this form, which is the logistic regression MLE formulation. So this, in fact, is yi log y predicted y. So if you look at here, connecting to the previous page, what I write. So this is actually predicted yi, right? And E, and this is summation yi log predicted yi plus 1 minus yi log 1 minus predicted yi. This is actually called cross entropy loss. Yeah, so I know there's a lot of derivations here. It's a little bit daunting. Yeah, so in fact, everything is the same as the basic Bernoulli. The only thing you do is to replace that p parameter into this parameterized form, and then everything is just an easy derivation. Okay, so in the modern logistic regression solver, people actually use second-order Newton-based approach. The reason is this type of logistic cross-entropy loss, you actually can have the Hessian estimated easily. Yeah, so please see the extra slides about how to write out something called a Newton-Raschen optimization, which is a second-order optimization method. So, and what we're going to cover in next class is to convert the logistic regression into some view like this. So we already know the first level is you just have a linear form, which is beta or W transpose X, doing a summation plus a B, and then you do a squashing function, squash this infinite minus infinity to positive infinity prediction into 0, 1. And it's logistic regression. So this is the second view. So there's a probabilistic view, there's also the squashing view. The squashing view can be totally represented just by a composition of a summation function and the sigma function, which is this function, which is this function. It's called sigma function. And the sigma function is an S-shaped function, which is the second view. And in fact, you also can add that cross-entropy loss, which I just derived, into one of the block in this kind of block representation. And then you can use stochastic gradient descent to solve it. And next class, we're going to cover deep neural nets, which is exactly just converting the logistic regression into summation module with a squashing module, and then plus some kind of error module, which we covered cross entropy today, by compose more layers of this type of summation and squashing into the architecture, and then with some kind of special structures, which is just the essence of deep neural nets. It's not complicated at all. What we cover today is the most basic unit of deep neural nets. The logistic is the summation module and the sigmoid module, and also that error output module